Good afternoon, everybody, or good evening, or good morning, wherever you are. I'm very delighted to introduce Professor Bijay Agrawal. He is working in Saha Institute of Nuclear Physics in the theory group, and since last few years, he has been doing some very interesting calculations, trying to connect uh, low energy nuclear physics data with the information from gravitational waves. And this is exactly what he's trying to let us through today in his talk. And if you have any questions, you can put them in the chat box, or you can wait till the end to ask, maybe raise your hand or something like that. So Professor Agrawal, the floor is yours whenever you're ready.
Okay. I would like to thank Dr. Panos for inviting me to this IRENA seminar. And I must also thank Chiranjeev for proposing my name. I'll be talking about constraining the tidal deformability from finite nuclear data. So essentially, I will show you some results which we have obtained, in last couple of years. Which shows that the correlation of tidal deformability with various nucleometer parameters depend heavily on the constraints imposed by the finite nuclei. And also we will, see that how the various finite nuclei data can constrain the value of tidal deformability itself. Now, as we know that the gravitational wave event GW170817 has opened a new window for the nuclear physicists. The gravitational wave which were observed by the merging of neutron star was the first time it was observed. Of course, the gravitational wave itself was observed in 2015 by the merging of the black hole. But for the first time in the case of neutron star, it was observed in the year 2017 August. Now this gravitational wave, one can infer the value of tidal deformability from the waveform of the gravitational wave. And this tidal deformability we will see depends on the equation of state of the dense matter, so that we can constrain the properties of the neutron star. And this GW170817 also produced the electromagnetic signal, and that was the first time that we have witnessed the site for the R process. Now this event is very important because the gravitational wave we observed almost after 100 years, and at the same time this site for the R process also we observed almost after 60 years of the seminal paper by B2FH. And today's talk basically I'll be concentrating mainly on the tidal deformability. So let us, maybe many of you know that what the tidal deformability is, but just for making my talk to be standalone, let us start with some few definitions of the tidal deformability. So the tidal deformability is nothing, but it tells you how much the star can be quadrupole deformed depending on the value of the tidal field. So in a way, this tidal deformability is nothing but a kind of a proportionality constant small lambda, which is related to the love number, that is kappa 2. So lambda is 2 by 3 kappa 2 times r to the power 5, where r is the radius of the neutron star. One defines for convenience the capital lambda, which is a dimensionless value, which is small lambda by m to the power 5, which is equal to 2 by 3 kappa 2 times r by m to the power 5, where r by m in the gravitational unit is dimensionless, and it is like 1 by the compactness factor. The value of kappa 2, that is the love number, depends on the ratio r by m and the quantity y, and this y is basically the solution of a differential equation. As you see here, it is r times dy by dr times plus y square plus y times f plus r square q equal to 0. And this quantity f and q, they depend on the profile of the pressure, energy density, and dp upon d epsilon for a given star. And you solve this equation for a boundary condition that y of 0 equal to 2, and this quantity, that profile for the pressure, energy density, mass, and the dp over d epsilon for a given star, that you obtain from the solution of the TOV equation. And we know that we need US as input to the TOV equation, which gives us this profile for the pressure, energy density, mass, and the dp over d epsilon. And that gives us the value of K2. And once we know the K2, we know the tidal deformability. So in a way, if we know the tidal deformability, we can get some constraint about the equation of state. So that is how that we know the gravitational waveform. From there, we can infer about the tidal deformability. From there, we can get some knowledge about the equation of state. And that is how we can learn something about the dense matter. One often defines the tidal deformability for the combined system because we are observing this thing through the merger. So it is, convenient to define this combined tidal deformability, which is nothing but the weighted sum of the tidal deformability of the two stars which are participating in the merging. So what you have here, lambda 1 and lambda 2, are the tidal deformability for two stars with some appropriate weightage. And the Q here is a ratio M2 over M1, where M1 is larger than M2. Now, one in the merger event, the chirp mass is basically very well known. So for a given chirp mass, if I assume some value of M1, I can get the value of M2 with the help of this chirp mass. So for instance, if we talk about this GW170817, one can see that for the chirp mass of 1.188, the value of M1 lies in the range of 1.36 to 1.6, and the value of M2 lies in the range of 1.17 to 1.36. Now, we know that most of the equation of state with the maximum mass of the order of 2m solar, for this kind of equation of state, we know that the radii in this range of 1.17 to 1.6 remain more or less constant. So, this radii does not depend on the mass. And if there is a spread, it's a very tiny spread is there. So we can assume that the radius is constant. So now if you recall the earlier slide where the lambda, so lambda 1 is proportional to something like R1 upon M1, and the lambda 2 is proportional to R2 upon M2 to the power 5. So we can say that the ratio of lambda 1 upon lambda 2 is proportional to the ratio of M2 upon M1 to the power 5, because R we have taken as to be more or less same. If you assume that we are using the same US for both the star. So in a way, one can see that lambda 1 by lambda 2 should be proportional to Q to the power 5. But here we have one additional Q dependence that comes from the mass dependence of the kappa 2. So what one gets is that lambda 1 upon lambda 2 is proportional to Q to the power 6. So we can express our lambda 2 in terms of lambda 1. So if we again talk about this GW170817, it turns out that if I talk about M1 to be equal to 1.4, then M2 from the chirp mass constraint comes out to be 1.33, and the Q is close to 0.95. So if I express my lambda 2 in terms of lambda 1 in the combined tidal deformability, that is lambda tilde on the top of the slide, and I can put Q equal to 0.95, so I can easily get that the lambda tilde is equal to 1.17 times lambda 1, and this lambda 1 is nothing but the tidal deformability for the mass 1.4. Now, why I am showing this relation? Because many times we will see that we are studying the correlation of tidal deformability lambda tilde with various nucleometer parameters, or we will take lambda 1 with various nucleometer parameter. So it does not matter whether we use the correlation study with lambda tilde or lambda, it is one the same thing because they are related by a constant. Now, let us just have a look at how the tidal deformability depends on the equation of state. So just as a typical example, I have taken this two of the equation of state. One is SLY4, which is based on the SCUM model, and this is a very soft TUS because the maximum mass is close to 2m solar. And other one is NL3, which is obtained within the relativistic mean field model, for which the maximum mass is close to 2.7. And you can see the tidal deformability is also very different for these two models. In particular, if we look at the tidal deformability for the mass 1.4, we see that the value is close to 300, whereas for the NL3, it is close to 1260. So in a way, if I know the value of tidal deformability, I mean, to a great accuracy, so we can really determine something about the equation of state. Now, I summarize here some properties for these two different equation of state. So what you see on the top is the neutron skin thickness, which is the difference of the RMS radii of the neutrons and the protons. And these quantities are basically calculated for the lead nucleus. And we see that for the SL4, the skin thickness is close to 0.16. And for the NL3, it is 0.28. Whereas the PREX2, I mean, this result has come out just about a month back, and they claim the value of 0.29 with somewhat larger error. Now you see that for the radii, for the mass 1.34, for the SLY4 is close to 12 kilometer, whereas for the case of NL3, it is 14 kilometer. And the value of lambda, as I said, is 300 for the SLY4 and 1260 for NL3. And the density at the center of the star for the SL4 is close to 3.5 times the rho 0. And for the case of NL3, it is 1.7 times the rho 0. So you can understand that the stiff equational state, the density is small at the center, the radius is large, and that is why it is very easy to deform it. And that is the reason that stiff EOS gives the larger value of the tidal deformability. Now, another thing we should note here is that the central density we are encountering for the extreme EOS lies in the range of 2 to 3 times the rho 0, where rho 0 is the saturation density, or I mean very close to the density at the center of the star. So I mean it is very easy to visualize that since we are talking about a star with the central density close to 2 to 3 times rho 0, so definitely the properties of finite nuclei can influence the property of the star, because the finite nuclei can really fix the behavior of the EOS all the way up to 1.5 to 2 rho 0, and the central density is hardly 2 to 3 rho 0. So that means the equational state, which is determined by the finite nuclei, can definitely control in a good way the value of the tidal deformability. Now, other thing you notice here that the SL4, which gives a small skin thickness, and this skin thickness is the property of the finite nuclei, and you can see the radius of the star is also small, the value of tidal deformability is also small. So one can really, and for the NL3, the skin thickness is large, the value of the radius is also large, and the value of the tidal deformability is also large. So this gives some sort of indication that the finite nuclear properties and the properties of star with the 1.4 mass cannot be independent. And that is what basically, we will discuss in the rest of the talk. So basically, we will see that how the correlation of this tidal deformability with the various nucleometer parameters are influenced by the constraint imposed by the finite nuclei. And then we will also see that how we can constrain the value of tidal deformability itself from the finite nuclear data, which are accurately known from the lab. So basically, the best way to introduce the nucleometer parameters is through the equational state, because these nucleometer parameters are the one which are the key ingredient in the equational state. So what I write here is the equational state, that is the energy per nucleon as a function of density and the asymmetry delta. So to a good approximation, one can decompose this E of rho comma epsilon of rho comma delta in terms of epsilon of rho comma 0, which is the energy per nucleon for the symmetrical matter, that is delta equal to 0, plus the density dependence of symmetry energy times the delta square. Of course, you can also have the higher terms proportional to delta to power 4, delta to power 6, but one finds that those terms basically doesn't affect the properties of neutron star in a significant manner. So most of the time those terms are ignored. Now this epsilon of rho comma 0 we can further expand around the saturation density. So the first term is the energy per nucleon at rho 0. Second term is proportional to k0, which is called incompressibility coefficient related to the double derivative of the E of rho comma 0. And likewise, the q0 is a skewness parameter related to the third derivative. Now we can also expand the symmetry energy around the saturation density. So, I mean, the first term is again the symmetry energy at the saturation density. Then we have slope L0, and we have the curvature K sim 0, which are nothing but the first and the second derivative of the symmetry energy. Now, as far as the quantity epsilon 0 is concerned, rho 0 and this J0, these are the quantities. I mean, epsilon 0 is close to minus 16 MeV, no matter what model you take. Rho 0 comes out to be always 0.16 per Fermi cube, and the J0 is the symmetry energy at saturation density, comes out to be close to 32.5, maybe with the error of, I mean, 2.5 MeV. So all these quantities can be very well determined from the binding energy and the charge radii of the few selected nuclei. Now, what we don't know with the, I mean, high accuracy is the value of K0, Q0, L0, and Ksim0. And this is what, I mean, we will try to see if we can learn about them from the knowledge of the tidal deformability. Now, this K0, as I said, is nothing but the 9 times rho 0 square times the double derivative of equational state for the simply nuclear matter. Q0 is 27 rho 0 cube times the third derivative. But I mean, I will not be talking about Q0 directly. Instead of that, I will take a quantity M0, which is nothing but the quantity related to the slope of the incompressibility coefficient. And at the saturation density, one can work out and see that this quantity is close to 12 K0 plus Q0. So I'll be basically, instead of considering Q0, I will talk about K0 and M0. And then you have the quantity L0, which is the, I mean, 3 rho 0 times the slope of the symmetry energy. And the K sim 0 is 27 is 9 rho 0 square times the double derivative of the symmetry energy. Now, these are the quantities we will be, I mean, trying to see if we can, I mean, constrain them from this value of the tidal deformability. Now, so basically, I'll be studying the correlation of these quantities with the tidal deformability by taking 28 different models. Of course, I will also show you the results which we have obtained with 3000 models, and the conclusion remains more or less the same. So with these 28 models which I have taken, most of them are basically, I mean, obtained by fitting the finite nuclei data and imposing some empirical constraint on the nuclear matter parameters. So the model which I have chosen, for them, the value of K0 is in the range of 200 to 300 MeV. The value of M0 is in the range of 1500 to 3000 MeV. And the value of L0 is in the range of 35 to 115 MeV. And the value of Ksim0 is minus 135 to plus 150 MeV. So they are, I mean, varying over a wide range, so that, you know, we can make the study, I mean, correlation study properly. And also the properties of neutron star are also varying over a wide region. The maximum mass ranges from 1.6 to 2.3, and the radius from 10.6 to 14 kilometer, and the lambda is about 100 to 1100 actually. So now, so these are the plots for the dp over d epsilon and the p over p versus epsilon. Just to, I mean, show you that all the equational state which we have taken, they basically, I mean, consistent with the causality limit. What symbol you see in the dp over d epsilon curve is, this is the density correspond to the maximum mass. So you can see at the maximum mass, my dp over d epsilon is less than 1. Only for maybe 1 or 2 cases, we marginally, I mean, overshoot. Our value is, you know, maybe 10% higher than the, I mean, whatever the limit we required is 1, so I may have 1.1. So these are the USS I have included for my correlation studies. And then we plot here the value of K0 as a function of lambda 1.4 and the value of M0 as a function of lambda 1.4. So, I mean, in the case of K0 and M0, we were not that lucky, and the correlation is not very, I mean, strong. In fact, these are rather weak correlation. But as far as L0 and Ksim0 is concerned, you can see there is a very reasonable correlation for L0. Of course, for the Ksim0, the correlation is somewhat higher, but definitely there is a meaningful correlation. So if we know the value of lambda 1.4 with higher accuracy, we can determine this quantity, I mean, as independently. I mean, so we will have the kind of, the value of L0 coming from neutron skin thickness and the value of L0 from the lambda. So we can really constrain this quantity more, I mean, in a narrow window. Now, these are my results, but then the similar calculation was performed by another group, and what they found that when they looked into the similar correlation as what we did, they looked into the correlation of lambda combined tidal deformity lambda tilde with K0, M0, L0, and Ksim0. And you can see that their correlations is very, very bad. I mean, K0, M0 is absolutely not correlated, and even L0 and Ksim0 also does not show the correlation, I mean, which is having some sense. And they did this calculation for lambda tilde with Q ranging from 0.73 to 1. And as I showed you earlier, that lambda tilde and the lambda are basically, I mean, related to each other by a constant. So even if they had done this study with lambda 1.4 as we did, they will not get the correlation as what we got. So now the question is that why these two results are, I mean, completely at variance. Of course, what they have done, they have taken more number of models, I mean more than 100 models, and these models were generated by varying the various nucleometer parameters, I mean over a narrow region, and these nucleometer parameters were randomly selected, and the correlation among various nucleometer parameters was ignored, and with the resulting nucleometer parameters, they constructed the, I mean, US of the Taylor expansion type, and then obtained these properties. So the question was that since we took only 28 models, is the number of model reason behind this kind of variance, or there is something else? So we wanted to analyze this, and what we did is we took something like about 240 models, which is, I mean, reported by Dutra in 2012. And these, most of the models again are consistent with the finite nuclei data, and various the nucleometer constraints were imposed. And we looked into the correlation of these nucleometer parameters, and we found that at least some of the nucleometer parameters like L0 and Ksim, J0 and L0, K0 and Q0, they were strongly correlated. Now, in the SCUM model, you can vary all these parameters independently, but still we saw that there is a correlation. And this correlation basically came because the models were consistent with the finite nuclei data. So we can say that this constraint on the finite nuclei data translate itself into the correlation among these various nucleometer properties. So if you are studying, if you are making any correlation study, and if you do not, if you ignore these correlations, that means you are somewhere not consistent with the properties of the finite nuclei. So what we did is that we took the typical values of these nucleometer parameters as normally employed in the literature, and we took the errors on these quantities at normally, I mean, one uses. And then we constructed these nucleometer parameters using a multivariate Gaussian distribution. And so you see here the pi are the various nucleometers, and the mu are the central value, and the sigma is the covariance among them. So if you talk about the diagonal element, then it amounts to nothing but the error on this parameter. So with the help of this mu and sigma, we constructed the multivariate Gaussian distribution. So we took two cases. Like in one case, we kept only the diagonal term of the sigma, all the off diagonal terms were zero, as was done earlier. And so basically, I mean, we mimicked the case of this Carson where the nucleometer parameter were completely uncorrelated. And then we constructed also another distribution where we introduced the correlation between L and K sim. That means the off-diagonal term in the covariance matrix sigma corresponding to L0 K sim 0 was kept non-zero, and it was adjusted in such a way that the correlation coefficient between the L0 and K0 becomes 0.8. And again, we generated the distribution. And now, out of these 4 or 5,000 models, generated, we filtered out only 3,000 models in such a way that all the models are consistent with the causality and the maximum mass is above 1.8. Now, you see here the result which we got here with these two different distribution. So what I am showing here is the confidence ellipsoid for L0 and K0 for the tidal deformability corresponding to the mass 1 m solar, 1.4 m solar, and 1.8 m solar. And you can see everywhere the MVGD1, which is obtained by ignoring the correlation among the various nucleometer parameters, the ellipsoid is thicker. Whereas for the MVGD2, that ellipsoid is narrower. So this clearly indicates that once we included the correlation between the L0 and K0 in generating our distribution, guided by the constraint from the finite nuclei, the correlation between the lambda and various L0 and K0 improved. In particularly, if you see for the case of lambda 1.8, the correlation of lambda 1.8 with L0 for MVGD1, what ellipsoid we get is almost looks like a circle. That means the correlation is completely missing. So basically, this clearly tells us that why the study which we made with 28 scum model, where the finite nuclei constraint were, incorporated through the fit, and the other study which was made, the results were at variance, because in the other study, though they took the large number of model, but the constraint which is imposed by the finite nuclei in terms of nucleometer parameter were not considered. So if you look at the table, you can clearly see the numbers here, and you see that always the correlation coefficient for the MVGD2 is larger than what we have for MVGD1, and in many cases the difference is quite large. So at least we understood that the finite nuclei can definitely influence the correlation of the tidal deformability with the various nucleometer parameters. So now, after having this correlation study done, so we realize the importance of finite nuclei. So you see here, what I'm plotting here is, again, I took those 28 models, and we are plotting for those 28 scum models, maximum mass versus the tidal deformability for mass 1.4. So in the panel A, what we have done, those 28 models, we group into 3 groups depending on the effective masses. So one group we made effective mass in the range of 0.6 to 0.65, and other group effective mass 0.65 to 0.75, and the third group 0.75 to 1. So you can see with the effect, and of course, we have also put the symbol plus and minus. The plus indicates that these are the, scum model where the isovector effective mass, that means the effective mass for neutron minus proton is larger than 0, whereas the negative indicates that effective mass for neutron minus proton is less than 0. So you see here that models with the smaller effective mass tend to give the larger value of the maximum mass and the larger value of the tidal deformability. And in any way, what we find that the range of the tidal deformability is, about 100 to 1100, as I showed you earlier. Now in the panel B, what we are doing, we picked out those models for which the ISGMR energies are consistent with the experimental data. So you see the hexagonal symbol. This is hexagonal symbols is put only on those US for which the isoscalar giant monopole resonance energy for the lead is consistent. So you can see out of all these 28 models, few models are basically consistent with the ISGMR energy. And the moment we put this constraint, the value of the tidal deformability restricts to basically 250 to about 700. Now we went ahead further, and then we also imposed the constraint coming from the peak value of the IVGDR energy for the lead. IVGDR means isovector giant dipole resonance. And again, we see that our number of the models which can satisfy this constraint becomes again less, and the value of the tidal deformability again gets narrower. Now, we further imposed the value, the experimental data for the dipole polarizability, which is nothing but the connected quantity connected to the inverse energy weighted sum rule for the IVGDR. So what you see here, triangle, are the one where the peak value of the IVGDR as well as the dipole polarizability is also satisfied. So the symbol with the hexagon and triangle means the ISGMR, IVGDR peak energy, and the dipole polarizability all are satisfied. And then you see the value of the tidal deformability is in the range of 300 to 500. So this simple exercise basically, gave us an idea that as you go on putting more and more finite nuclei constraint, you cannot vary the value of the tidal deformability in a wide range. So basically we carried out a fit where we really imposed all this data as a fit data. So we took a scum model and we put usual binding energy and charge radii into the fit. But on the top of that, we also added the isoscalar giant monopole resonance energy. And we also added the peak value of the IVGDR for few nuclei and also the dipole polarizability for 48 calcium, 68 nickel and tin and the lead. And we also added the value of the maximum mass in our fit data. And all of these are directly the observables. We carried out the fit and then we found out that our all the fit data are nicely reproduced by the scum model, and the resultant model gave the value of tidal deformability close to 267. So that means if you put all this finite data, all this data on the finite nuclei together with the maximum mass, then at least within the scum model, the value of the tidal deformability for mass 1.4 m solar will not be too different from 200 to 300 actually. Now, then we did our, now since the parameter, now the new parameter which we got, you can see that since we put the value of ISGMR energy and the maximum mass in our fit data, you can see that the error, the value of sigma on the incommensurability coefficient K0 and the Q0, which are usually high, came out to be low. So again, we perform that, this previous study, again, we constructed with this kind of input, the multivariate Gaussian distribution and incorporated the correlation among various nucleometer parameter and compared our result with the one which we got directly from the covariance analysis. Because in the covariance analysis, I can directly get the confidence ellipsoid for between any two observables, and we see our multivariate Gaussian distribution result and what we got from covariance analysis, they are almost, very close to each other. And of course, this is not very surprising because when we perform the covariance analysis, we basically we expand the chi-square function only up to the quartic order. We keep only up to the second derivative of the chi-square, and all the higher order terms are ignored. So basically, whatever assumption, so basically we assume that the parameters are having the Gaussian distribution. So when we constructed the MVGD by explicitly constructing the Gaussian distribution and what we got from the covariance, they are consistent with each other. So this basically, gives us the confidence numerically we were not wrong anywhere. Everything was fine. And you can see here, interestingly, that the correlation of tidal deformability as the mass goes up, the correlation with L0 slowly decreases. Whereas with the K-sim 0, as the mass goes up, the correlation increases. Why? Because as we go for higher and higher mass, we would require the density, equation of state of the higher and higher density, and higher density equation of state will be also governed by K-sim 0, because at the lower density L0 is enough, but as we go up in density, the K-sim 0 also starts contributing. So that is the reason here that as we go up in the mass, the correlation with K-sim 0 increases and the correlation with L0 decreases. Now we did one more exercise that to really see that how much we can accommodate in the scum model the value of the tidal deformability. So whatever we had scum model with SK lambda 267, in that model along with our fit data, we also put the constraint on the value of tidal deformability to be 500. We demanded that the value of tidal deformability should be 500. Again, we fitted, we got the new parameter set, we call it 484 because the resultant parameter set gave us the value of tidal deformability to be 484 as we demanded 500. But then if you notice, you see here that basically the binding energy charge radii, I mean, we got more or less same. Even ISCMR energy also is fine. But we found the marked shift in the value of the tidal deformability. The moment we demanded high value of the tidal deformability, that the alpha d, that is the dipole probability, that shifted up. And just you can see in the graph also, I plot here the value of alpha d for this two different parameter set, SK lambda 267 and SK lambda 484, along with the external data with the error bar. So you can see that SK lambda 484, I mean, the value of alpha d is quite off, even sometime beyond the error bar. So basically it tells us that if we try to push the value of tidal deformability within the scum model, I mean, to the very high value, then we will be compromising with the finite nuclei properties, which are very accurately known. So with this, basically, I mean, I have come to the end of my talk. So basically what I showed you that the correlation of tidal deformability with various nucleometer parameters are greatly influenced by the finite nuclei constraint. If we treat them properly, we see the strong correlation. Otherwise, the correlation disappears. And we also saw that the tidal deformability for mass 1.4, I mean, a tidal deformability basically correlation of lambda with L0 decreases as the mass of neutron star increases, whereas the correlation of lambda with K sim 0 increases as the mass increases. And then I also showed you that if we really take an extensive set of data, which included the giant monopole and giant dipole constraint together the maximum mass, then the value of the tidal deformability is constrained to around 200, I mean 267. And of course, I have not showed you the error. The error, if I calculate theoretical error within the covariance analysis, it comes out to be close to 100. So I can say that between somewhere between 200 to 300, we can get. And if you want to push it beyond that, we will be compromising with the properties of the finite nuclei. So, and I would like to at least, I mean, here are my collaborators. So you see the top three, Tuhin Malik, Chiranjeev Mandal, and Nausad Alam. They are my PhD student. They really helped me very heavily in carrying out these works. And other are my colleagues, Konstanka, Jayande, and Santosh Samadar, and 14. I have been working with them for quite some time. And these are the results which I showed here. Thank you very much.
Okay, the floor is open for questions, comments.
Yes, I have a question.
Yes, please go ahead.
How can you reconcile your results with the P-Rex2 measurement?
Actually, what we found that even if I take the limit of lambda 267 to 484, that our skin thickness are in the range of 0.15 to 0.21. So if I really try to, I mean, get the P-Rex result, then I won't be getting the property of neutron star correctly. And if I try to get neutron star correctly, I won't be getting P-Rex2 correctly actually. And this is what everybody is finding. I did not show you the result. Recently, Philip Landry, he also showed from the, I mean, effective field theory calculation that if they try to constrain the nicer data and the value of tidal deformability from LIGO Virgo, they get the skin 0.15221. This is what precisely I get from the SCUM model.
Okay, thank you.
So it looks like the P-Rex2 and the neutron star, whatever we have at present, I mean, they really don't go hand in hand.
Any other question? If not, I can ask a question. Because what he has asked regarding the neutron skin thickness and the neutron star properties, as you just said. So do you think it is also the time we need to look into the SCRM models? Maybe they are at fault to, I mean, they are limited by their functional form or something like that. Do you think we should go in that direction as well?
Actually, as far as the, I mean, correlation of skin thickness with L is concerned, if we accept that correlation is really strong and that exists, this puzzle cannot be solved. I mean, only if there is something else, I mean, contributing to skin thickness other than L, then only we can, I mean, solve the problem. I mean, even I also heard, I mean, people are now questioning even the correlation of skin thickness and L. They say this is just the outcome of the mean field theory.
Okay.
So maybe something beyond mean field can solve the problem.
I see there is a hand raised by Dr. Prakash. You can speak up.
Yeah. Thanks for a nice talk. I have a question aimed to annoy you with a purpose. Suppose, for the sake of argument, we say a phase transition occurs of one sort or the other around 2 times nuclear density.
Yeah.
So what would your take on that would be?
Yeah, of course. In my entire calculation, I have not considered the phase transition, and I mean, definitely the phase transition would change this. I mean, result little bit, but if it occurs at 2 rho 0, but if it occurs at 3 rho 0, then my all the results will be more or less intact.
Okay. Also, your results are more or less confined to 1.4 solar masses. Suppose we were to discover higher than 1.4 solar mass stars, then we would be hard stretched to carry out SCRM analysis at higher densities. Would you say that?
Yeah, that is true. I mean, whatever I have showed, I mean, though I have also considered 1.8 solar mass, but the result beyond 1.4 solar mass is likely to change. I mean, because of the phase transitions and other things actually. So that's why, I mean, I mainly focus on 1.4 because that is something which I feel will remain stable.
Okay, fair enough. Give my regards to Jishnu. I know him from a long time.
Sure. It is really very nice for me to talk to you.
Thank you.
So I have another comment and question.
Yeah, please go ahead.
Okay, I don't want to be critical, but I will be critical. I think one serious shortcoming of your study is to use a maximum mass constraint in it, because these equations of state are not applicable above twice the saturation density. Things can completely change, and so a SCRM parameterization that supports only 1.6 solar masses may be perfectly adequate for densities below twice nuclear density. So I don't think that you should be using maximum mass constraints in an analysis of this form.
Okay.
And another comment I have is that regarding the P-REX experiments, I think one has to take seriously the uncertainty they associate with their measurement. And actually the result is not 0.29 plus or minus 0.7, it's 0.28 plus or minus 0.07. And so at the 1 sigma level, there is no incompatibility between the P-REX experiment and your results.
Yeah, I mean 0.21 will just touch their limit.
Yeah, so that's at 1 sigma.
Yes, exactly. Yeah.
And I think we can't be firm about anything unless we have a 3 sigma result.
Exactly. Yeah, and that I agree that in the extreme case, I will have just overlap between my skin of 0.21 and the P-REX of 0.28 minus 0.07. Actually, yes, you're right.
Okay, thank you. I enjoyed the talk.
Yes, thank you very much.
I just have a small doubt regarding the first question you asked, that the scar models are limited by limited up to say 1.6 or 2 times rho zero. What do you mean by that? It's the implication of the phase transition or something else?
No, what I meant is that these are parameterizations fit to the properties of nuclei. Therefore, they only probe the properties of matter up to the saturation density. And technically should not be trusted beyond that point.
Yeah, that's true. I mean, beyond 2 we should try to, try to test different kind of polytropic equational state or some other thing. I mean, because beyond.
So this fits in with Prakash's question and comment about a possibility of a phase transition. So all kinds of stuff could happen above twice saturation density. And so to use a constraint based on what a maximum mass prediction of from an equation of state that's valid only up to nuclear density, I think shouldn't be taken seriously.
Yeah, that's true. That's true. That's true.
Any other questions, comments? If not, we can close the session and thank Professor Agrawal for this nice presentation and the discussion also. So have a nice evening, night, or rest of the day, whatever you have left.
Thank you very much. Just a quick note for the people, the JINA Gather Town Room will be open after this presentation. So whoever wants to continue the discussion and or interact, you can follow the link that I posted on the chat and join the Gather Town room.
Okay.
Thank you very much, Dr. Thank you very much, Dr. Agrawal, for the very nice presentation and for accepting our invitation.
Yes, it's my pleasure. Thank you very much.